If you, thank you. If you can take your seat quietly, I'll start off with some announcements. My name is Federica Bianco. I'm serving as the Science Collaborations Coordinator and co-chair of the Transcendence and Variable Star Science Collaboration, and I will do the announcements for you today. So this is our second day of the conference, and it's also photo day. So please make sure that you are at 5:30 with your LSST t-shirt that you received with your when you're registered by the pool. We will take the photo of the meeting. We will actually take a few photos of the meeting, the photo of all the participants and some subgroups. We are trying to do this in a spirit of inclusion and fostering the diversity of LSST. So we provided a sign-up sheet for people that wanted to have the group that they identify with taking an additional photo. We did that last year as well. We did a women or people who identify as women photo to show LSST representation at the International Women's Day. We'll do it again this year. We also will have a photo for all the undergrads and a photo for the people that have families with them here. So make sure that if you belong to any of these groups, you stick around for your photo to be taken. And make sure you're wearing your t-shirt. If you have accessibility needs, contact the research desk and make sure you're on time at 5:30. After that, we'll have the meetings reception at 6 p.m. It's a short walk or possibly shuttle ride from where we are, and you have a drink ticket in your badge, so remember to bring that. Tomorrow, we'll have the Unconference. The Unconference is a free session, a free-form session that is designed to catch all the things that we haven't put in the schedule as organizers. So the topics of the Unconference are proposed by you. Anything that you think should be discussed can be proposed. There is a board right outside of this room where you can post those ideas and you can vote for the ideas that you think are more interesting to you. Multiple sessions can happen in parallel. You can also jump between one session and the other. It's extremely free form. Some proposals have already been put up. One is related to things that will be discussed today, the low Earth orbit satellites impact on LSST. But there's a number of other options and other proposals. So please make sure you propose what you think should be in the conference and is not yet in the conference, and vote for the proposals that have already been posted and will be posted. The deadline to post the proposal is tomorrow at lunch, and the event is in the last session tomorrow. Another thing that happens tomorrow is Storytime Domain. So this is an effort organized by the EPO, an outreach effort where people that are involved with LSST, so all of us, are filmed talking about their LSST experience, the role in LSST, and particularly the prompt this year is to tell the camera and the audience about a recent win that they experienced with their team. This happens on Wednesday. There is a sign-up sheet that will be posted so you can pick up one of the time slots. And it's extremely informal, extremely easygoing and friendly. I did it last year. It's very fun. It's in Coronado 1. Please participate. If you have registered and you have dietary restrictions, please remember to get at the reception desk the tag that indicates what your dietary restrictions are. This facilitates you getting the meal that you want and need. Also, while you're at it, if you're in a science collaboration, pick up the sticker for your science collaboration. You can have more stickers if you belong to more than one science collaboration. I designed the stickers. So any complaints or compliments, come to me. Thank you very much. And those are conversation starters. Some people are in the same science collaborations, but they don't know each other, they don't know each other's face. So if you see somebody with a sticker of your science collaboration and you don't know them, please stop, say hi, and introduce yourself. Breakout slides. Right, so if you are chairing a breakout session, you owe us one slide about your breakout session. The plenary on Friday will be dedicated to reports from the breakout sessions. So make sure you upload the slide, you have the link here, you probably were contacted, actually you certainly were contacted by Rampal, you probably noticed that attempt to contact you. If you didn't go, look for it. It's a very short report on what you did, 1 minute, one slide. Everybody that is chairing any of the parallel session owes us that. This is particularly dear to me because it's the LSST at Europe meeting, which will happen next year in Italy, which is my home country. I'm on the SSC. I'm chairing the SSC with Giovanni Bono and Adriano Fontana. If you have any questions about the meeting and you're interested to come, please catch me while I'm here. The meeting will be in June, June 8th through June 12th. It will be hosted at the Accademia dei Lincei, which is Galileo Galilei's alma mater, no less. And it's really in the historic center of Rome, so that should be a lot of fun. There is a bare-bone website available. More information will be uploaded on that website very, very soon. Also, LSST is hiring, so don't forget these hiring announcements. Technical job as web designers and web developers, engineering job as senior software engineer and software engineer, so multiple levels of software engineers experience, and also commissioning verification science on the science side. For all of those, you can contact Rampal if you have any questions. Which brings me to today's agenda. At 9:05, which I believe is past, but for the next 5 minutes, we will have Michael Wolvesis pitching on the difference image analysis workshop that he has organized for this meeting, which will happen in multiple sessions in the next few days. Tony Tyson will talk about the impact of low Earth orbit satellites on the LSST images. And then we will have 4 presentations by 4 science collaborations. This will be repeated tomorrow with the remaining 4 science collaborations for a total of 8 science collaborations. Today we'll have solar system, galaxies, active galactic nuclei, and transient and variable star science collaborations. An older version of the schedule had informatics and statistics science collaboration in the last slot. There was a swap. That will be tomorrow. So that's the plan for today. Michael, take it away.
Good morning. LSST is key thing is studying the changing sky. And one of the big techniques to do that will be looking at differences between images, whether it's successive images or just against a template. So difference image analysis is a key part of the science that LSST will do. For full disclosure, I do supernova, so of course I'm a little biased, but that motivated me to, with some others, organize a set of 4 sessions that we'll have this week exploring difference image analysis, which by the end of the week you will call DIA, just like all the other people who currently annoy you. So there are 2 sessions today that are really about pixels and pixel level algorithms and about gauging performance of how well we're doing. So the first will be the basics. So if you actually haven't thought about this at all, we'll have some tutorials about how basically image subtraction works and the theory, like with math and convolution symbols and things like that. And then we'll also talk about the tests that we should do, to validate and measure our performance. At 3:30, we'll talk about resolved and moving variables and transients. So this is if you thought the first session was too easy, what if your source is extended? What if your source is moving across the sky? So yes, it's a point source and an image, but you want to put them together. What if your source exploded hundreds of years ago and its light is now bouncing off dust clouds in the Milky Way reaching you, a light echo? What if your source is a comet against a crowded background? All right, so we're going to talk about those fun things at 3:30. On Thursday, we're going to talk about data products. So if you, for example, wish to say, hey, I trust that people will do great things with pixels. I want to know how do I access the data. Come to those sessions. So that's alerts in year 1 and beyond. And so that will be talking about, on day 1, do you have a template? What should you do? At day 100, I've observed a field 20 times. What statistics should I calculate? At day 10, I've observed a field 3 times. Should I calculate a structure function? Maybe not, right? So what are those data products going to come out? What makes sense? And this is where science contributions can be very useful. And then the data products. So currently, for example, in the DPDD, there's not a product called a light curve. What should a light curve look like? Do people agree? Should it be some different things? So I encourage you to come to these sessions, and I've included in the notes just for you to quickly look, but these are basically exactly what it says in the abstracts. But just to remind you, to make it real simple, these are all in Joshua Tree. So that would be simple to remember. And I would point out to you if I were not a little turned around. But I trust you will find that. And I just want to mention one more thing. So while alerts and brokers and automated observations are not formally a part of the workshop, this is very much in the air. Brian Miller will be organizing a session this afternoon to fill in between the two, DIA1 and DIA2, about advances in the alert follow-up system, from Brian and I assume Rachel Street and others about that. Hotwiring the transient universe is next week. Presumably, if you're going, you already know that you're going. But it's very much going to be about this. And there's a community broker workshop talking to them about alerts. These are all live links that I encourage you to follow up if you want to look at. So these are the sessions. If you care about pixels and information theory, come and learn great, cool things today about how to do all that stuff. If you trust that all that's going to be fine and you just want to know what the data come with your science use cases on Thursday to those sessions. Thank you.
Make sure you turn your mic on. Okay, so let me tell you something really scary. Although I think that there are ways out of this debacle, at least in the short term, but probably not in the long term. That's the executive summary. So for purely economic reasons, it pays to explore the possibility of low latency links from low Earth orbit satellites so that you don't have the long 1 second latency to geo. And so a lot of companies are exploring this. And one of them, SpaceX, has launched the first 60 of their eventual 12,000 satellites in low Earth orbit. And you probably have heard about them because they were easily visible to the naked eye. And my wife and I saw 57 of them zipping past not too many nights ago at 10:30. So the challenge is, of course, that is the reflected sunlight and twilight. And this is, if you go to starlink.com, I recommend it highly. It's a very entertaining, very nice website showing these solar arrays unfurling. These have now been moved up to 550 kilometers. They plan to launch many more of these in the coming months and years. Some at this altitude, and then another constellation at 320, which, if you do the math, is a whole magnitude brighter than the reflected light. As you might see from this, they are shiny. They are unpainted aluminum currently. We've been talking with this SpaceX engineers, and the good news is that they really do want to help us. How exactly they're going to do that, we're all trying to figure out. It's not easy. This is what their bus looks like. It's not a giant cube. It's a very thin kind of thing. What you're looking at there are some of the antennas, the phased array antennas that are used for uplink and downlink. But it's unpainted aluminum currently, and all sorts of little facets to reflect off of. CSPASA did a simulation of the progressing twilight as the terminator moves past the zenith, which is right there. And if you look right now, you can see one of the Starlinks passing past the terminator. And this is the distribution of opportunities to do astronomy at night as a function of time of year, also from CSPASA. And the star is where an observation that I'm about to show you was made by Todd Borison with a bunch of 40 centimeter telescopes following some of the star links. According to the calculations, it should have been pretty invisible, but it turned out to be fifth magnitude. But you can see here from this plot that although this was done for Los Angeles, the latitude is very similar to Cerro Patron in Chile. And you can see from this that in the summertime, wherever you are, you have precious few hours to be free of these things. But in the winter, it's much more easy to have nice long observations. So this is the one of the 5 photometrically calibrated images that Todd Borison got for us using the LCOGT telescopes. 4 of the 5, when reduced, agreed within 1/10 of a magnitude of each other with regard to the surface brightness of this trail. This is from Starlink BK. The 5th one was off by 1/2 a magnitude brighter for reasons that I don't understand, but it could have been a partial glint. At any rate, the surface brightness of this, when transformed onto the seeing and the size of the 8.5 meter collecting area at LSST, puts us about 4 magnitudes brighter than the CCD saturation level on the LSST. So what we decided to do was to try to simulate this in the laboratory on the same CCDs that LSST is going to be using. And this is what it looks like. What I did is I just went to the shop and said, okay, make me a mask that's 1 PSF wide. I had to translate that into inches. And then we mounted that in a re-imaging facility. This is with the expected background level of LSST observations in a 15-second exposure. And of course, what happens when you, with LSST, and also with Borison's telescope, you go to some place in the sky and the thing just zips past because it's moving quite fast. We saw in our backyard the other night one of these every 1.6 minutes. So they're moving that fast. Anyway, so this is what it looks like when you actually do the experiment on one of our CCDs. And the trail, as I mentioned, when you transform Todd's photometric measurements onto our system, results in about 200,000 electrons per pixel along the main trail, which is, we have decided on the project to reduce the gain of the camera to the point where the A to D, the analog to digital converter, is on scale for something that's beginning to saturate in bloom, which is good because that means that we can at least attempt to remove the crosstalk. The crosstalk that you're seeing here, all these little parallel tracks, those aren't satellites. That's capacitive coupling between the output video from the one channel, which is the main channel that you see there. This is a log display, by the way. And the adjacent video channels. This is simple capacitive coupling in the connector and the ribbon cable right after the connector. About 2 picofarads for the nearest neighbor. And you can see, I can see, looking at the screen, maybe you can't, on the projector, I can see 4 fourth order crosstalks. Now, we are doing experiments. This is just the very first one to see how well we can do removing the crosstalk and then seeing if the correlated noise, it'll still be correlated, along that line gives rise to some artifacts damaged LSST science. And one of the ones that's sort of obvious is that for stars, there's no net alignment of the correlated noise. It's all sort of like circular and it cancels out. But for a linear feature like this that appears on many of the CCDs, there's a net apparent shear correlation function of the noise peaks if they're detected as fake galaxies. And so we want to do all of the experiments necessary to simulate all this in the lab in the coming weeks, and it should be straightforward. This is due to the hard work of Andrew Bradshaw. There are also other artifacts that you can see in the lower left here that we don't fully understand, and so it's not a simple picture. We would actually rather get rid of the problem. Now, the radio pollution is something that the Starlink engineers can address. We've been having meetings with them every couple of weeks, and they can turn off their transmitters when they're over the SKA, which is sort of delightful. They can't turn off the sun. And so what are they going to do? I'll get to that in the Q&A. There are other issues having to do with these low Earth orbiting satellites. Occasionally, and very briefly, they are at an attitude that the entire backside of the solar array reflects the sun down to your telescope. And that's a Starlink flare, actually, at station, and that's Arcturus, zeroth magnitude down on the bottom. So it's minus a lot of magnitudes. And I personally haven't seen these, although I've been looking, but the amateur astronomers who do look a lot harder say that they're still flaring occasionally. So this is going to be very rare. We can probably just dump the exposure and go on. I don't think it worries us too much. This is their plan. You can find this very chart if you go to Wikipedia. This is their plan filed with the FCC, and you add those numbers up and you get 12,000 of these on a time scale of LSST survey. So, this is not the full story, as I alluded to initially. By the time LSST is on the sky, this is the way the sky is going to look, according to Pat Seitzer, who looked up these same numbers. Amazon has a similar system that they're about to launch called Kuiper, and in different phases, and that's the different colors. The Starlinks are in pink, and you can see that it's getting crowded, but not hopelessly crowded. That is to say, if these folks gave us the orbital elements exactly updated, we would know where not to look. And there's enough spare sky to avoid these things without slewing terribly fast, zipping around. But it's potentially a problem if the full plan constellations of all the various different companies comes to pass. This is not all of the current filings with the FCC. The current filings with the FCC are closer to 20,000 satellites. And those are just the companies in the US. I know Samsung is going to put up 6,000 of these fairly soon. They don't have to file with the FCC. There are Chinese and Russian and other constellations. If you add all these up, as people do, you're getting closer to 40,000 of these things in the mid-LSST survey time period. At which point, there's pretty much nowhere to hide, although you can still do it if they give you the exact orbital elements. But it would begin to impact the scheduler a little bit. So one of the things that one could do is to paint these black. Now, I don't think that all of these companies are going to be so nice, but the SpaceX people really do want to help us. And we've recommended that they paint certain parts of these things with Aeroglaze Z306, which would give 3 magnitudes fainter albedo. And that would go a long way to solving that saturation problem. Occasionally, an exposure would be saturated, maybe a few percent at a time or less. You could just dump the exposure if you wanted to. But whether the other companies, other outfits follow suit is an open question. Certainly, if SpaceX elected to do this, then it would, the other companies might feel some moral obligation. The point is that there is no international body that governs this. Where there is an international body that governs radio interference called the International Telecommunications Union. The IAU has no regulation with regard to light pollution from space. And so I think personally we need something like that, and this would be a good thing to pursue in a longer timescale. But unfortunately, what you're looking at here, and its evolution over the next few years, is going to happen. And it's going to happen, I think, on a timescale short compared to any kind of international regulations. That's my guess. And let me leave you with another problem of the same sort. Mainly, most of the domestic flights in Chile fly right over our observatory site, creating contrails which sit around through sunset and twilight and give us a problem. So we're not out of the woods with regard to the foreground pollution issue. One could imagine, again, dealing with folks on this issue. So with that, I'll just leave it open for questions. Thank you. Microphones at either side. There's also apparently going to be an unconference tomorrow afternoon where people can.
Right, there is an unconference proposal to talk more about satellites and their impact on LSST. And it seems like people are question shy at this meeting, so I'm going to start. Oh, yeah. Michael is going to start. I'll repeat the question.
We can hear.
The microphones are stationary on either side.
Yeah. That's the next step.
I think you said this briefly, but tell us a little bit more about how long any given satellite is visible into the evening. You said you saw one at 10:30, which is a scary number.
I didn't expect it, but it depends really actually on where you are with regard to twilight at the observatory, where you're observing from, and where the satellite is. It could be a different place. And so you would therefore want to have a strategy where you observe towards the dark side, towards the night, as opposed towards the sunset or sunrise. That would gain you another maybe half hour or so. Yeah.
There's one more question I saw coming first. In the interest of time.
Yeah, it depends critically on the season.
Do we understand why they were so bright initially on launch? It seems like they've dimmed a lot, and it's...
Yeah, it's 1 over r squared.
That's it?
Yep.
Wow.
Also, that together with intentionally did not have attitude control. They weren't articulating them as they now do at station. So there were a lot of cases. If you looked at that picture that is on the web everywhere from Lowell Observatory, each one looked a little bit different in brightness because the back of the solar panel is different orientation.
Let me briefly, we've run out of time for questions, but let me briefly add that there is an issue of space sustainability as well that I think the solar system people are best in this room to address. There's a lot of stuff in space. Space sustainability refers to the fact that we need to know where that stuff is to make space safe and sustainable. And unfortunately, painting them black will go sort of against that concept. But I think in this room we have the expertise to evaluate the pros and cons. So I think the unconference will be a good place to do that. We are gonna move on. Thank you, Tony. with the science collaboration presentations. So let me introduce Eric Shaw, who will present for the Solar System Science Collaboration, very apropos. And the science collaboration presentations will tag along. So Eric, please introduce Sugata next. And then it will go on like that.
Okay, hello. All right, thanks, Federica. Yeah, I'm happy to be able to speak to you all today, so thanks to the organizers for making time for updates from the science collaborations at this meeting. So I am Henry Shea. I am with the Planetary Science Institute, which is headquartered here in Tucson, but we're all over the place, so I'm personally based in Honolulu. I'm the Software and Infrastructure Development Working Chair for the Solar System Science Collaboration. But I'm giving this summary on behalf of the SSSC co-chairs, Meg Schwam, who's in Belfast, just recently moved from Gemini over to Belfast, and David Trilling at Northern Arizona University. These slides are mostly from Meg, so if you like the talk, if you don't like the talk, it's mostly her fault. But if you do like it, it's probably, I guess it's her fault also. So the first thing we were asked to address in these talks are what LSST can do for your science. So for solar system science, this is a table that comes from the LSST science book, which is by now probably a little out of date, but it's still probably good enough. But the gist is that we're expecting about an order of magnitude increase of most key solar system object populations. So, maybe 100,000 NEOs, 5 million or 6 million main belt asteroids. We expect to get lots of observations of them, repeated observations, so we can do things like light curves and phase functions and things like that. We expect to go down much smaller, as you might expect. And also get long arc lengths, so that will help us with studying orbit evolutions for things that have orbit evolution, and also be able to accumulate enough data for light curves and things like that. So we'll get UGRIZY photometry, and I just have a note here that because we don't actually know size distributions, especially down at the low end, it may change. This leads to large uncertainties in the actual number that we'll probably find. So that's why we need that's why we need LSST. In terms of individual science cases, there's I'm just gonna highlight a few that were mentioned in a couple recent white papers, Cadence white papers, excuse me. So first of all is we can explore the populations of main belt comets and active asteroids. So these are objects that appear to be cometary, so they show activity, but their orbits are asteroidal, so they mostly are in the main asteroid belt. So this is a bit surprising and interesting. We think that some of the activity is due to actual sublimation. So this is actually icy objects in the asteroid belt where we don't necessarily expect them, because most comets come from the outer solar system. But some of this activity may also be due to impacts or rotational disruption, so things just spinning themselves apart. So at the bottom, you just see some images of some of these objects, some examples. The plot shows a recent work that showed that, so this is an example of a science question we might be interested in. There's some indication that MBC's, main belt comets, might have their orbits, their perihelia, aligned with that of Jupiter. And it's small number statistics. There's only you can see the number of lines, like 5 or 6 that seem to show this. But if LSST finds many more, we can test to see if this pattern holds and whether this tells us something about their dynamical behavior or source of their activity. And the plot on the right shows that we expect most of these to come to perihelion in the north. So this came from our northern ecliptic spur white paper, showing that we need some northern coverage for the LSST. So moving along, many of you may have heard either through talks or even from the news that there is some indication of a large planet in our outer solar system, and this was inferred by, again, similar to the main belt comet situation, there's an alignment of, or a rough alignment of orbits of extreme trans-Neptunian objects that are, yeah. So you can see these diagrams. So the MBCs, their orbits seem to be aligned because of Jupiter, and these objects seem to maybe be aligned by some unseen planet 9 or planet X, sometimes people call it. So again, LSST will help us hopefully discover many more extreme TNOs and then see if, again, if this pattern holds and if, it's not due to some sort of observational bias. And finally, I think is the last science case, we want to be able to find interstellar objects. So some of you may be aware that about 2 years ago, a Pan-STARRS telescope, which many of you are probably familiar with, discovered the first known interstellar object. So this is an object from outside our solar system that entered our solar system, and we were able to, spot it in time that we were able to, get off a few observations. So some of this will require follow-up. So some of the, these super dense light curves obviously will require dedicated follow-up observing. But things like colors, in the far right plot, could possibly be done with LSST. But but even just finding them would be good for triggering these observations. So yeah, so this is really exciting stuff. We expect not that many, but 10 over the life of the mission of the survey. So yeah, so I mean that would be great since we only have one so far. Just to show you some of the work that the collaboration has been doing, we put out a science roadmap a while ago, but this year we published a software roadmap, and so this was in research notes of the AAS, so it's pretty short, it's just 2 pages, but it basically lists a bunch of tasks that we need to do, and is broken down in like urgent stuff we need in the first year, so we need to be working on it right now, and other tasks which are for later in the year. Also important, not quite as urgent perhaps. And then this was followed up by a much longer archive-only paper where we kind of dug into those tasks a little more and said what kind of software exists, what we need, and what kind of approaches we might take. So in terms of active efforts by the collaboration, we have been running yearly readiness sprints. So these are just like little mini workshops. We've had 2 so far to get people together to collaborate and work on projects. We are preparing for commissioning, science data, and follow-up. So we want to identify and work on the needs now in terms of our needs now in order to be able to do science later. Many people here are working on metrics, so we're working on solar system metrics for cadence decisions. And we also have efforts by just individual members to do preparatory work, developing their own personal software, working with ZTF, or writing funding proposals. So I have a shout out to Mario here because I think everyone agrees he's great. So he's an SSSC liaison between the project and the collaboration, basically, and he's got lots of roles. It's very busy. So we have a website. It's down at the bottom, and it has more information for people who are in the collaboration and want to know more, or people who are not, who also want to know more. So there's lots of good information there, and I will, yeah, I'm almost done. So in terms of future activities, so at this meeting, we have 2 dedicated sessions later today. Actually, it's the second morning session after this, after the coffee break, and then right after lunch. The first one will deal mostly with science topics, and the second one will deal mostly with pipeline and cadence-like topics. And as Michael mentioned earlier, we will also present a little bit in the difference imaging session at the last session of the afternoon. So it's a very solar system heavy day. But then I get to relax. So we also have a meeting or workshop at the upcoming European Planetary Science Conference, and the Division for Planetary Sciences, that's a AAS planetary science meeting, the annual meeting. So this is a joint European-US meeting in Geneva next month, actually. And so we'll be having a workshop there to try to encourage more people to get involved. So in terms of, this should maybe be like future needs. So funding, I think this will be a recurring theme in the upcoming updates as well. So we need funding for travel support and salary for people who are on soft money, because a lot of these people who are interested in working on LSST but can't afford to, basically. We were given enabling science funding for our first sprint, and this was pretty successful. We had about 25 attendees with diverse backgrounds and career levels. In 2019, we applied but didn't get the funding this time, and so it was a smaller group, less diversity. So funding would be great for getting more people involved. So we can make do with a small amount of money to kind of get these sprints going, but we will need more, of course, to kind of do really meaningful preparation for LSST. So that's all I have. Thanks. Oh, and next will be Sugata talking about Galaxies.
Okay, thanks, Henry. Let me start by thanking the organizing committee. So thanks to the organizing committee for making time for the science collaboration reports at this meeting. I think hopefully this will be useful for the community to see what's happening. So I'm the chair of the co-chair of the Galaxies Science Collaboration. So I'm going to give you a summary of the aims and goals that we have, and then I'm going to give you some highlights of work that we're doing in preparation for LSST data, commissioning data, and then the survey proper 2 years from now. And then I'll touch on some of the main issues and challenges that we have, which are going to be similar to what Henry mentioned. Okay, so I think it's fair to say that LSST will revolutionize the study of galaxy evolution. So we're going to be able to study the evolution of the extragalactic universe, over cosmic time in unprecedented detail, and we're going to do things that other surveys simply haven't been able to do. One of the important things about LSST is that it's going to open up unexplored regimes. Okay, so one example is the low surface brightness universe, which I'll describe in more detail later in my talk. Whatever future surveys you're doing at other wavelengths, your optical counterparts are going to be coming from LSST. And I think the convergence of data from surveys like LSST and cosmological simulations or theoretical models that we have today are going to be transformative in understanding the physics of how galaxies form and evolve. So revolutionary advances are expected from LSST, but as I'll show you, there are some challenges that we have to overcome before we can actually fulfill the potential of the survey. Okay, so the aims of the science collaboration are to organize, obviously, the science effort, the Galaxy science effort within the community, to produce high-level data products, so things which will enable people to actually use and analyze LSST data. And of course, we want to influence the scientific direction of the survey by providing input into the project, for example, on commissioning survey fields and things like that. So we have a broad membership. It's drawn from across the world. So we meet via regular telecons. And I think it's worth pointing out that some of the topics that are sort of close to our heart are featuring heavily in recent international conferences. So, for example, there was an IAU symposium last month focused purely on the low surface brightness universe, which is going to be one of the key topics of LSST Galaxies work. Okay, so we have a roadmap which is on archive, and our activities form the basis of the first, I believe, Nature Reviews Physics roadmap, which was published last month. So I invite you to have a look at these documents if you're interested in what we're trying to do. So let me give you some highlights. So this list is not exhaustive, but these are areas where Galaxies Science Collaboration members are putting a fair amount of effort in. And the effort is going to producing preparatory, this is preparatory work to create pipelines that the community can use, so tools and methodologies that the community can use to actually analyze and use LSST data. So these are the 4 topics I'm going to cover: low surface brightness science, machine learning and artificial intelligence, simulations, and photometric registers. Okay, so let's start with low surface brightness science. So as I mentioned in my first slide, the low surface brightness, the LSB universe, is one of the things that LSST can do better than any other survey. So why is this regime important? So the low surface brightness regime, which includes, by the way, the dwarf regime, so dwarf galaxies are sort of cosmological distances. So these dwarf galaxies and these low surface brightness galaxies, they dominate the galaxy number density, right? So if you don't understand how these guys form, well, you don't really understand galaxy evolution in general. Okay, so these galaxies, so dwarf galaxies at cosmological distances are only marginally detectable in surveys like, say, the SDSS. Okay, so it's only LSST which can give you, huge tens of thousands of these dwarfs, which you need to understand galaxy evolution. So apart from these dwarf galaxies, there are LSB structures. So there was some discussion of these tidal features, for example, which are induced by mergers in the undergrad session yesterday. So these merger-induced tidal features encode the assembly histories of your galaxies, right? So they tell you how the galaxy was assembled hierarchically, if you like. And so by studying and understanding the properties of these tidal features, you can essentially build up a picture of how these galaxies are forming. And of course, then this constrains your hierarchical paradigm, the theoretical paradigm that we have. Another type of LSB structure which constrains the paradigm is intracluster light. So if you think about galaxy clusters, actually a significant fraction of the baryons in your galaxy clusters are in this diffuse component between galaxies. Okay? So what we would ideally like to do is understand how the intracluster light evolves. We want to characterize the ICL, we want to understand its properties, we want to understand its evolution with redshift. And this is something that LSST in principle will be able to do. So that's all great, right? The low surface brightness universe is waiting to be unveiled by LSST. Of course, there are some technical challenges. And one of the biggest technical challenges is that because these structures are faint and diffuse, they are extremely susceptible to sky oversubtraction and also shredding by deblenders. Okay, so here's an example. So if you look at the image which says original, so this is an image of a cluster from the HITES PREMCAM DR1 survey. And you can clearly see sky oversubtraction, the darker regions along these bright and extended sources. So we need algorithms which will actually fix this problem, because if you don't fix it, you're missing a lot of the LSB flux, and you can't actually do your science. So this is an example of a potential fix. This is work by Lee Kelvin et al. So what they've done here is they've essentially fitted 2D Sursich models to each of the sources, which allows them to characterize the flux in the wings of these sources. And then they get a feel, so that allows them to get a feel for where the threshold at which the sky oversubtraction sort of kicks in. And then they are able to use that threshold to sort of add the flux back in, and then you get something which looks like the corrected image. Okay, so it kind of works. So of course the challenge is to build these algorithms into the main data pipeline of LSST, right? So the problem is not that you can't do bespoke sky subtraction like these guys are doing here. The problem is actually putting these things into the main data pipeline, so everyone can. These types of things are done automatically, if you like. Okay, so moving on, so machine learning. So I think it's fair to say that the data volumes from surveys like LSST, so 20 terabytes per night, the analysis of these types of data sets is going to require automation. Okay, so automation is certainly going to be desirable, and I think it's going to be needed to analyze data from things like LSST. So I think there's a growing convergence between astrophysics and computer science, right? So people in the Galaxies community are actively borrowing tools and techniques which already exist in computer science, and we're trying to develop pipelines which will enable us to analyze LSST data using machine learning. So let me give you an example. So let's talk about galaxy morphology, right? So morphology is a pretty fundamental parameter. So you need to know what the morphology of galaxies are for basically the full spectrum of galaxy evolution studies. But morphology also cuts across several science collaboration, the topics that several science collaborations are interested in, because it's a key prior for 4D pipelines. And it also provides you with contextual data for transient light code classifications. Okay, so this is the kind of thing that lots and lots of people are going to be interested in. Now, typically you would do morphological classifications visually, right? You would just eyeball your image and type your galaxy, is it a spiral, elliptical, blah, blah, blah. But of course, with LSST data volumes, you can't do that. Okay, so it's very hard to do visual classification of these kinds of data sets. And LSST's short cadence is probably an extra hurdle, right? Because repeatedly producing training sets that you might need for supervised machine learning may also be difficult. Okay. So one of the solutions is to try and build unsupervised machine learning algorithms and then do your benchmarking visually after the fact. So here's an example. So this is work by Gareth Martin et al., who's in Arizona right now. So what this algorithm does is it essentially groups objects like galaxies based on properties like texture and color. Okay, so each column is a morphological cluster. So the point is that objects in each column are grouped together. And so in this case, this is an implementation on the HyperSupremeCam ultra deep layer, okay, which is similar to what you're going to get from LSST tenure depth data. And you can see that the algorithm's doing fairly well, right? So things which are, objects which are in the same column sort of look similar. So you get elliptical spirals, et cetera, separating out quite well. So this kind of algorithm can also auto-detect rare objects like shells in the top row, rings and accretion events, and it can also start looking at low surface brightness dwarfs in your data. But I think it's fair to say that more development is needed before you can sort of let these algorithms loose on LSST data. So this is work for the future, essentially. Okay, so let's talk about simulation. So to understand, to use the LSST data, to understand how galaxies form and evolve over time, we're going to have to compare this data to simulation. So in the last decade or so, there's been an advent of hydrodynamical simulations in cosmological volumes, right? Cosmological simulations are important because you have a large-scale data set, okay? So you want to understand, so you want to have a model which simulates a large enough volume, i.e. cosmological volume. So you might have heard of some of these simulations, Horizon AGN, Illustris, Eagle. So these are popular models that people use. The problem with these models is that, so this generation of models doesn't really have the mass or the spatial resolution to compare to a data set like LSST. So for example, the spatial resolution of these models is about 1 kiloparsec. And if you think about the scale height of the Milky Way disk, it's 300 parsec, right? So you're not really resolving galaxies well in these cosmological simulations. So essentially we need higher resolution simulations, but in cosmological volumes. Okay, so here are some examples. So this is a simulation called New Horizon, which has 40 parsec resolution in a cosmological volume. So there's a mock LSST GRI image on the left, and you can see a sort of collage of images, mock images seen through, let's say, SDSS, JWST, et cetera, et cetera. Okay, so there are going to be simulations like New Horizon, others like Illustris TNG50, and these will be important theoretical counterparts to LSST. So a lot of people are working on building these simulations, calibrating them, testing them, using HyperSupremeCam data so that we are prepared to use them when LSST comes around. All right, so the last thing I wanted to mention was photometric redshifts, right? Now, photometric redshifts are important for pretty much all science collaborations. Now, if you want to do galaxy evolution science, then what you need are physical parameters, right? Like stellar mass, star formation rate, rest band colors, et cetera, et cetera. Now, the problem, of course, is that the spectroscopic redshift coverage within the LSST footprint is going to be pretty sparse, especially at the beginning of the survey, right? So a lot of the statistical studies that people are going to do, certainly in the Galaxies collaboration, are going to need photometric redshifts. And so it's interesting to ask the question, how good are these photometric redshifts, right? Especially in the, let's say, the dwarf regime, where LSST is really going to give you data that no other survey can. So interestingly, if you look at the HSC, the HyperSupremeCam DR1, it suggests that photometric redshift accuracies, the fractional error, if you like, in these photos, is about 10%, okay, for dwarf galaxies. And that's pretty impressive because that redshift accuracy is coming mainly from the fact that your data is deeper, okay? So the tools that we have already available to us applied to these new data sets could give you photometric redshift accuracies, which are good enough for you to do statistical studies of galaxy populations, certainly at low and intermediate redshift. So investment in photometric redshift pipelines is essential, and members of the Galaxies collaboration are working on these PhotoZ pipelines. All right, so let me finish off by just mentioning some of the issues and challenges that we have. So I think the main issue we have, or the main challenge that we will have, are data rights, right? So a lot of the stuff that I've shown you is being done by non-US and non-Chilean members of the Galaxy Science Collaboration. And so if these guys lose data rights, then it could have a crippling effect on how prepared we are when LSST data starts flowing in, let's say, 2 years' time. We will need commissioning surveys which give us the area and the depth that enable us to test our infrastructure. I think that's going to be very important. It's particularly important for low surface brightness science. So there are some pipelines which have already been developed, as I've just shown you, but I think scaling these pipelines up, integrating them within the software stack is going to be a challenge, and I think we're going to need help from the project to do this. And I just wanted to echo what Henry said. I think that the lack of funding has generally hampered the prep work that we've done. Okay, so it'll be great if we could have more funding to employ people to build these pipelines, scale them up, integrate them with the software stack, et cetera, et cetera. Okay, so this is my last slide. So I hope you'll agree that some of the stuff that I've shown you cuts across many science collaborations. So we are always interested in new members joining, helping us with the work that we're doing. And the best way to get involved in any kind of Galaxies work is to join the collaboration. The membership has increased rapidly in the last 6 months, which is good. So we have a Galaxies session on Thursday at 3:30 in Coronado 1. So please come along if you're more interested. If you're interested, I'm here all week. So if you have any questions about Galaxies science, just come and find me. Thank you. And I'm going to hand over to Franz Bauer, who's going to talk about AGN.
Okay, there we go. Right, so I'm Franz Bauer from Universidad Católica in Chile, and also Millennium Institute of Astrophysics. And I didn't put any leadership up here because we're actually in like this weird state of flux with the science collaboration, so I'll get to that in a little bit. But I'm sort of one of the ranking, thanks. Fine. I'm sort of one of the people who's contributing, and so I was sort of tapped to give this talk. Just to put everything in perspective, LSST full-depth image, something like this. We're going to have 18,000 square degrees of this. And I show in the middle, essentially, the UDF size. So the Hubble ultra-deep field of something like 11.5 arc minutes squared. So we're going to get 5.6 million UDFs. That's non-trivial. And so we're going to have 20 billion galaxies, 17 billion stars, and in those 20 billion galaxies, we'll have something like 300 million AGN that we potentially could detect. The optical portion of that will probably be something close to 75 million. That's a lot compared to, say, the 1 million that Sloan has found. And so there's a lot that we can do with that, just to sort of put this in perspective. So one of the challenges is just the selection, finding those 75 million amongst the 20 or 30 billion sources that are there. And so we can go traditionally with multicolor selection, as was done in the past. We can also look at astrometric properties to sort of rule out some of the problematic contaminants. But we also have the ability to do variability studies for the sort of significant portion. And so we'll have something like 55 to 180 samplings over a 10-year period. And these will be a very very effective complement to the color selection. Both the color selection and the variability work when the AGN luminosity is kind of above the host galaxy luminosity. And so as we get sort of fainter and fainter and have that mix, it becomes harder. And then the other potential area would be just multi-wavelength. So you can see the SED over there. And so we could select things based on essentially the multi-wavelength properties from the radio to the X-ray. So we'll have color, we'll have variability, multi-wavelength selection. These are going to provide different slices through the AGN population and ideally allow us to get a pretty complete picture of what AGN are doing, how they're growing over cosmic time, how they are relating to their host galaxies, how they are potentially providing feedback for the host galaxies. So this is just a sort of example to put things in perspective. So on the, let's say, I guess your left is something from Demetrio DeCecco. It's a VST 2-meter R-band survey. And on the extreme left, you have essentially a 5-month analysis of 27 visits, and you detect, this is in the Cosmos field, so you have some X-ray coverage, and they detect about 15% of the X-ray sources. And then they completed a 3-year analysis with 54 visits and ended up getting about 60% completeness with respect to the X-ray sources. And so you can see essentially all the sources that are above the RMS are considered variable. So this alone would give you an estimate of something like 250 AGN per square degree. And so extrapolating that to LSST, this is already 5 million, and this just goes down to sort of 23rd magnitude or so. So LSST is going to go down every visit. We'll get down to 24th magnitude or so. So this is sort of to bracket your expectation. On the other side, the right side, we have HST looking at Cosmos, or no, sorry, at Kendall's field. And this is a 2 to 10 year analysis going down to something like 26th magnitude in Z-band, or the equivalent in HST, 850 LP. And they end up only finding sort of 4 to 10% completeness versus the X-rays. You can see on the bottom plot the sort of overlap of the sources they detect in red, the sources where they have variable sources that aren't detected in the X-ray in blue, and then the overall X-ray selection in gray. And so we miss a lot of the X-ray selection, but we have a sort of unique slice through that population. If you extrapolate those numbers, that's about 2,000 per square degree, or 36 million. So LSST is probably going to deliver hopefully something in the middle there, but maybe even closer to what we get with HST. And so, you know, we'll have longer baselines, more and deeper epochs, more bands, better fidelity to do host sort of deblending with the nuclei. So we could potentially get a lot just from the variability study alone, in addition to the color. So just to sort of look at some of the science, I'll point people to the LSSC science book, chapter 10, which has all of this in great detail. And so there's not really time to go through this. But on a nightly basis, we're going to be able to monitor all 75 million AGN, or some fraction thereof, of which at least 5 million are going to be variability selected. We're going to discover something like 50 large AGN flares per night, be it from blazars or from accretion disk instabilities. We should expect something like 3 tidal disruptions per night, possibly about 1 strong quasar microlensing event every 10 days. And then maybe, very rare occasions, we might actually see a binary supermassive black hole in spiral and merge. But we don't know the rates of those. We don't know how often we don't even know what to expect, really. So just put a pin in that. Longer term statistical studies are, we have all of this variability information. And so we can do massive statistical studies of variability characteristics of AGN. So you see the structure function in the middle plot there, showing as the structure function versus the Eddington ratio for various AGN. This is from Sloan from Quasar Studies, from Chelsea McLeod. And so we'll be able to expand that in virtually every parameter that we can think of to really understand and characterize accretion and the variability of accretion disks. There'll be the LSST versus time domain spectroscopy synergies. And so we'll be able to do things like reverberation mapping studies, doing photometric reverberation mapping and broadline emission reverberation mapping together. Possibly even, if we include multi-wavelength studies, possibly even using AGN as a standardizable candle and being able to probe the Hubble constant out to high redshift. There's accretion disk structure, which is shown in the bottom there, looking at time lags as a function of color to understand, again, the statistical properties of accretion disks. Small separation binary supermassive black holes, seeing them either as periodic signals or as astrometric movement. Then there's transient fueling of essentially dormant supermassive black holes, so these tidal disruption events or other things. And then finally, the selection of high redshift AGN and the possible constraints on black hole seeding mechanisms, how black holes are formed, how they grow and evolve at early times. So that's our sort of principal science goals. The AGN Science Collaboration currently has 57 members. We have monthly telecons, breakout sessions at AAS, EWAS, et cetera. We welcome new members. You guys are welcome to sign up. Right now, well, basically we've gone through, it's been a bit difficult to have some people, some people do the international sort of collaborators, given the data policy issues, data rights, and the funding model, it's been very difficult to sort of assemble and motivate this group of people. We're presently working through where we're sort of at a loose confederation level in terms of our structure, and so we're revising our membership and our organization structures to become something like a hardcore collaboration, which is sort of what we'll need. And we're looking at a tiered membership model similar to TBS. So we're now essentially ratifying the policies, and so this month there's no leadership at all, and then next month we'll kind of build up from scratch. And so we're inviting new applications probably from the end of the week to come join us. So this is just a couple pictures of us at the AAS in 2017 in Texas. In Chile, we have yearly meetings, and then the UK AGN and Galaxies meeting in Cambridge. And then we have a breakdown of sort of the membership as a function of country. Where are we going here? It lost it. Let's go. Yeah, I'm going to use the error. Oh, it just froze. It's not good.
Somebody signed in with another Google property tab. Let's see if we can get back to where we were. Was this the last slide you had?
No, it's not. It's like the middle slide. Okay.
How far?
No. There, that's good.
Go ahead and drag.
Okay, so roadmap. Basically, we have a living document sort of prioritizing our critical AGN science goals. There is a lot of work to do in basic AGN selection, analysis of LSA simulations, detailed science planning, et cetera, et cetera, et cetera. And there's a lot of cross-collaboration of work to be done. And so I just highlighted in Cyan all of the different working groups, the project, the data model, deblending, all the SCs. Just to sort of, I'm going to go through some of the things we need to do, and I'll put the sort of synergies we have with the other science collaborations alongside it, so you can see, ideally, this is to motivate the other science collaborations to talk to me and say, hey, let's actually start to work together. Because as the AGN group, we've had some problems with sort of doing that and having the inertia to do that. So lots of things to do with selection, characterization, classification. Establishing training sets, we're kind of in the middle of doing that right now, and then we're also collecting more data to build up essentially truth tables in the deep drilling fields. So we have some idea of all of the AGN possible from the various selection methods, and we can see how well we do in terms of completeness and reliability of selecting AGN. Even something as simple as determining a color and host nuclear separation, we have to determine what that means in the LSST context. And this is in relation to the Galaxy Science group, working group. How deep can we actually probe into a host galaxy to detect an AGN or not? And even in difference imaging, can we detect this in variability or not? Generating realistic simulation catalogs, ideally with collaboration with some help from Desk. Exploring different machine learning mechanisms with the informatics and statistics collaboration. Testing the effects of cadence. Working with light curves, trying to detect the variability and quantify the variability, looking at it in terms of difference imaging. So working with TBS and the data model group. Then we have redshift estimates. So again, similar to the Galaxies, we need to establish training sets. We need to determine what properties actually are the most useful. And identify the best methods, empirical or SED fitting, et cetera, depending on source type. Test the effects of the different cadences on the FOTZ accuracy to see if there are problems there. Produce and store essentially PhotoZ probability distribution functions. So rather than having a single value, having a distribution function and propagating that through. This is sort of non-trivial and needs work in order to sort of have it move through all the processes to drive reliable errors at the end. Then we have the variability science, the physics, so simulating AGN light curves over a range of black hole mass, Eddington ratio, redshift, cadence, et cetera, et cetera, et cetera, to understand how the properties we're seeing in the variability and then the reverberation mapping, how those are actually recovered and how our completeness and understanding develops from that. Assessing how extreme rare objects or periodic signals can be detected in realistic AGN light curves, developing and studying how host subtraction techniques might impact, say, the detection of TDEs, tidal disruption events, or binary supermassive black holes, and then feeding these results from commissioning and from our early studies back into our classification selection algorithms to hone that over time. And then finally, the follow-up. And so working with the brokers to efficiently, reliably classify the AGN so we know what we're looking at and can trust it. Developing strategies to trigger follow-up observations of all these variable events. Developing a strategy to target rare outlier or high redshift AGN for classification and to then fold it back into our classification techniques. And then finally, developing a strategy to essentially do long-term monitoring with spectroscopic campaigns. So there's a lot to sort of do there. Two approaches so far that have been successful have been, well, one of the big problems is the lack of funding that particularly US and even in Chile we've had. These have posed major roadblocks for the science preparation that we've been able to do. And so we've sort of tried to be creative about getting some funding from other sources to then sort of use to do AGN science. One approach has been to sort of bootstrap our way along using the deep fields that we already have good data for in Stripe 82 from Sloan, and then folding in now PanSTARRS and CTF. And then eventually folding in DES and Hyper Supreme Chem when those data releases sort of become a little bit more stable. And then finally moving into the LSST regime. The second approach has been to gather the multi-wavelength data. We've been fairly successful at doing that for the deep drilling fields. And so we've been able to get XMM and Spitzer data, so this is what's shown in the bottom, over most of, or a sizable fraction of the deep drilling fields, which will be useful for training sets and truth tables. And there's a lot more data to come. So the future, progress has been slow. There's a variety of factors. They'll be reiterated over and over with each science collaboration. Lack of funding is a big one. The mindset that LSST is not here yet is also another one that's hard to motivate people. Inertia of working with the other science collaboration groups is large. And so we need to sort of work together to get some liaisons that we can actually reliably trust and will do work. And then the uncertainties and limitations around the data rights and data access, which is sort of a demotivating factor for international collaborators in particular. So we're looking to have some initial multi-tiered static and temporal training sets available by the end of this year, and then begin machine learning data challenges essentially through the different archive data sets, hopefully sort of scaling up to LSST level data over the next 2 years. So thank you. And so I'll also introduce Fed, who will talk about the transient variable science.
Right, now with my hat of Transient and Variable Star Science Collaboration co-chair, together with Rachel Street, who is from the Scumbers Observatory and who is also here at the meeting. The Transients and Variable Stars Collaboration deals with anything in the sky that changes, so that's a lot. So I like to start with this phase space diagram of the transient sky, which is biased towards transient as opposed to variable, as the case is. This particular version is the version that we had in the LSST most recent paper version by the LSST ISSC 2019 paper. And sort of it's an updated version of an existing plot that shows the phase space of transients. On the x-axis you have time scales for transients, not really the lifetime of the transients. Think about it more as the relevant time scales for variability in these transients. And on the y-axis, you have a measure of the energy of the transients, so brightness, magnitude, on the left and on the right. And the take-home point from this plot is that it's really packed. There is stuff all over the place. And the Transients and Variable Stars Collaboration deals with all of this stuff. So transients that have time scales from less than a day to years, and transients that have energies from 10 to the 35 to 10 to the 50 Earth. So we really deal with a lot of objects and phenomena that are different, both physically and phenomenologically. This particular plot is a really intriguing one for people that are interested in transients and in LSST, because you see the space where I had space to put the legend, the short time scales, low energy things, which is an unexplored region of this space. And the LSST will have the opportunity to explore it, but also to explore the regions of this phase space that are all the way on the other end of the plot, the very long time scales, due to the 10-year timeline of the project. we deal, the things that LSST will bring to our science collaborations that are really unique have to do with the event rate for transients. It will increase the size of the samples by so much that it will bring subclasses of transients into the realm of statistics. For example, rare types of supernovae. Supernova is one of my specialties, so these slides are slightly biased towards that. It will be statistical samples of events that are really rare, like tidal disruption events, and in that we have an interest share with AGN and kilonovae. It will detect precursors of transients that now we know may exist, but are faint or rare, and we don't see them. Precursor of, for example, core collapse supernova explosions, or precursor of luminous blue variables, stellar eruptions. It will go down to magnitudes that are fainter than we did before, so we'll get higher redshift and we'll reach spaces, regions of the evolution space for these transients that we haven't reached before, for example. And also in space, we'll have a larger sample of phenomena like microlensing. We'll be able to see microlensing across the galaxy, and we'll be able to see supernovae farther away than we have before in statistical samples. And we'll have long-term, multicolor, relatively dense time series that will allow a better characterization than ever before of a number of transients, pulsating variables, magnetically active stars, for example. And these are just very few of the examples of the phenomena that we deal with. Of course, our science is extremely sensitive to the specific details of the observing strategy, which, as it is, are not really settled on. So differences in the simulated observing strategies for LSST, the proposed observing strategies for LSST, will give you radically different time gaps between visits, which really dramatically would affect our ability to study a particular phenomenon, perhaps improving the ability to study a phenomenon, but really precluding the ability to study a different one that acts on different timescales. Here you have some plots of, at this point, relatively old simulations of the LSST survey, which show you how much it can the time gap between observations can vary. You have the intra-night gap and the inter-night gap on the left and on the right, respectively, gaps in the same filter and in different filter, in any filter at top and bottom, respectively. So as a result of this, we've been very active in brainstorming strategies that would work for us, for each one of our transients and variable phenomena with LSST, including considerations on aliasing, color information, filter selection, light curve density, exposure, etc. And this is reflected in the fact that we have a massive submission in the white paper call last November. We submitted 40% of the papers were led by TVS members. We also have proposed TOs, which is a relatively new concept, but it's being embraced by LSST as an option to follow up particularly gravitational wave alerts, so pushing LSST into the multi-messenger astronomy realm. And Tony Tyson will actually talk about this, more of this on Thursday, as well as during the public talk tomorrow night. Largely, we depend on follow-up observations, co-observations, statistical and synergistic data and collection and data mining with other surveys at other wavelengths or other or in different regimes of the electromagnetic and non-electromagnetic spectrum. So we're very involved in the creation and evolution of development of the brokers, as well as everything that follows from the LSST down the discovery chain of astrophysical phenomena. So brokers, classification, target of opportunity managers, everything that links us to the observing facility that will do the follow-up. Not all of our phenomena require follow-up, but a very large swath of them does. As an example of our involvement in this, we've been involved together with DESC on the plastic challenge. We've provided some of the set of data that were used as training and testing data in the plastic challenge, which was a challenge through Kaggle led by DESC with a significant contribution of TVS to classify transients in LSST-like light curves. And it was an extremely successful project, the first most attended astronomical Kaggle challenge in history. A little bit about the structure of the science collaborations. We have two chairs, myself and Rachel Street. My expertise are in extragalactic transients, and mostly Rachel's expertise are in microlensing. We have a number of subgroups. We're divided in 15 subgroups. Roughly, we can group them in extragalactic, fast transient, supernova, tidal disruption events, galactic, interacting binaries, magnetically active stars, microlensing, transiting exoplanet, pulsating variables, non-degenerate eruptive variable, and here you see that we also deal with what we call geometric transients, phenomena that are not intrinsic to the object that we're studying, but are effect of projection, transients and occultations, transits and occultations, as well as sort of methodological groups, cosmology, classification, multi-wavelength characterization. You see some groups are grayed out because currently they don't have active participants, they don't have a leadership that is pushing the work of the subgroups, so they do exist in a sort of dormant state, quiescent state. And this is the breakdown of our members that can participate to more than one subgroup. In fact, every member can need to apply to a primary subgroup and can apply to up to 2 secondary subgroups. And the distribution is interesting because, for example, as primary classification, you see that, as primary category, you see that classification is the second most common. But if you go back, classification is actually a dormant subgroup. So classification people wake up and work. We also have a number of task forces that we organize every year to approach more present and shorter time scale problems. Last year was the first year we had the task forces, and we had four very successful task forces that dealt with organizing the white paper that were presented to the proposal call for surveys for LSST survey strategies, where we presented 14 white papers. We have an active task force that studies stellar variability in crowded fields, which was active last year and is continuing through 2019. We have a TVS roadmap. I'll tell you a little bit later about this, and a task force about brokers that organized a first survey to brokers and broker users, and is continuing now with a second survey to broker and broker users. I'll also mention that in a second. Currently, we have 4 task forces. A task force is that is writing the metrics for the papers that we have submitted in the white paper proposal call, a math task force, the continuing of the stellar variability in crowded fields task force, a task force that parses the access to the science platform and to the Stack Lab specifically for TVS-related science, and a commissioning task force that is organizing commissioning ideas related to LSST, transients and variable stars. A little bit about the broker requirement survey, because I think that is of interest to many people here. The first survey connected, for the first time, comprehensively the users and the brokers, and got a broad idea of what the users needed and what the brokers were planning and where the discrepancies were. I extracted one particular pie chart, donut chart, from this survey, which I thought was interesting and was discussed earlier during the SAC meeting. How important is that brokers classify your transients? Generally, most people think that it's really, really important. On the other hand, when asked if people are ready right now to write a simple filter that would allow them to get notifications about their transients, the majority of people are not really aware of that, highlighting that really on our end, the users, there is a lot of work to do in preparing for LSST. This is a really crucial point when you get 10 million alerts per night, that you can select with simple choices what are the interesting ones to you. The current task force has another interesting question, which is, do you really need those 60 seconds, the 60 seconds or less latence in the alerts? So do you really need your alerts from LSST to come at you within a minute of observations? The LSST system is capable of doing it. It was designed to be capable of doing it, but that does put a lot of stress on the system. So if we really don't need the 1 minute latency, if we can relax that to maybe 5 minutes, that seems like a good idea. So we're asking the community, do you really have a science case for the 60 seconds? And we have one. It's fast radio bursts that could be observed in coincidence and then trigger another observations in the radio within about 2 minutes from the first detection. So that is the only solid case that I can see from this survey that really require 60 seconds. But you'll see that there's more than one answers to that. People that are doing gravitational waves are asking for those 60 seconds, but that is not really scientifically justified in the justification because the latency of the process of gravitational wave characterization after the trigger is actually quite longer than 60 seconds. If you have a science case that really needs 60 seconds or less, well, less than 5 minutes, please answer to this survey. It's still open for you to give your answer. We have an ongoing roadmap that we're writing. The variable part is largely finished. The transient part is lagging behind, mostly my fault. I don't expect you to read our index. I just wanted to show you that it's going to be a long document. I was shooting for less than 10 pages. That's not going to happen. We do a lot of different science. Our roadmap is very large, very different, and very diverse. We have a number of meetings. Recently, we had meetings in the US, in Europe. We have a significant participation of Europeans, particularly Italians, recently to the science collaboration. We participated to meetings that were not exclusive to TVS. The Flatirons Cadence meeting had a large TVS presence. A meeting in Palermo had a large TVS presence designed for specing special programs inside of the white paper cadence. We're organizing the Transients and Variable Stars and Stars Milky Way local volume joint meeting at the University of Delaware, which is my new home, October 14th through 18th. We also have a deblending with Scarlett in Naples meeting that is relevant to TVS and led by TVS members in October, and a Supernova Across Science Collaborations meeting, which is TVS desk, Galaxies and Stars and Milky Way joint effort. Both of those are sponsored by the corporation. And we have a parallel session at this meeting, which will happen on Friday, 9 to 10:30 a.m. in Presidio 1. The last thing I'm going to mention is that we're also reorganizing and restructuring our science collaborations. We created in the past year a new code of conduct, the first code of conduct of the science collaboration, not new one, the first one. A charter which defines our structure and governmental structure and the aim of the science collaboration. And we're still working on the publication policy. Turns out writing a publication policy is quite a little bit harder and more controversial than writing a code of conduct or charter. But we're working on it. We have a panel that is now going to take on the challenge of finishing this up. We also had intra-collaboration agreements. The first one we established with DESC for the purpose of the plastic challenge. We hope to see more of this because we hope to foster more intra-science collaboration activities. Maybe I'm not even going to bother with the main issues because they're the same that you heard for all the other science collaborations. We don't have funding, so largely the amount of work that we put in this, especially on the governmental side, is free. We're volunteering our time. Rachel and I are volunteering our time as chair. All the chair of the various subgroups are volunteering their time. Concerns about access to data for international members and difficulty in organizing intra-collaboration work just due to organizational issues. And I think I can stop here because I think I'm out of time. And maybe we are just at the end of the session, but if you are patient, we'll take 5 minutes and I'll invite the speakers for the session. So all the science collaboration co-chair that spoke, Sugata and Eric, please, to come up in case there is a question. Maybe we can take one question per science collaboration if you have any. Thank you, Mike.
This is a question to Henry. You did not mention the Starlink scare of satellites, and in particular, one of the things that Tony said is, "Oh, we'll just look away from the sun in twilight," which is exactly where you want to look for near-Earth asteroids. I don't know if you want to comment.
I guess contrary to what Fed said, I personally don't know much about that topic, but I think probably some of the MOPS people here might be able to comment on that, like Mario or Lynn. I know there's some discussion on the Slack channel about that topic, but I haven't dug into that much. But probably a good thing to discuss at the science session next.
Any other questions?
Sure.
Thank you.
For Sugata, hey, have you talked much with any of the other collaborations about the machine learning strategies you're all doing? I mean, that's a huge cross-cutting thing. I'm sure a lot of other collaborations are thinking about it too.
Yeah, yeah, you're right. I think there isn't enough crosstalk between collaborations. So we haven't talked much with other collaborations, but I think, yeah, we should. Everyone should.
All right. I don't see any more. Maybe I see one question in the back. Did I see that? No. I don't see any more questions. Thank you for coming. Yes, Pat, thank you.
So tomorrow there's a session on machine learning algorithms applied to blending challenges. And so blending is a place where there are a number of efforts involving machine learning, and there were some discussions of that at last year's blending workshop. There'll be the session tomorrow, and with that, and we have a blending task force within the Dark Energy Science collaboration, but we've hosted a number of talks from people from other collaborations, in particular Galaxies. So there's a nascent kind of cross-collaboration efforts there, but I think it could grow, and we may want to have a workshop just on that topic, for example. So people should come tomorrow for the machine learning and blending, because Jim Bosch will be there to give some reality checks on this too, which I think is important.
And with that, I want to thank you for participating to the plenary session. Noah, please go ahead, Tony. Sorry.
Responding to Michael's point, he's absolutely right. I didn't mention all of the impacts scientifically of the LEOSAT issue. It completely excludes the ability to look into twilight, which is what we would want to do during that period of time to detect near-Earth threatening asteroids. So we will not be able to do that. Even if we paint them black.
I was commenting very quickly. I just remembered, so I think Eric Christensen is here somewhere, and he's with Catalina, so he would probably know a lot about this topic. So you could find him or come to one of some sessions, or we'll figure it out and tell you all about it.
And vote for the unconference if this topic seems interesting to you. With that, I want to thank you. Remember the photo today, the unconference, all the announcements that we had at the beginning. And we'll see you in the next plenary that starts at 10:30. Okay, session 11, that starts at 11.